Hello, everyone. Sorry, I might be somewhat sleepy. I just got up, so if there are any mistakes that I make while I'm speaking, please excuse them. So I have to give a parental advisory before I give this talk, because I don't want people to spend their youth on trying to find them. This is a very sparse class of bugs. You will take a very long time finding exploitable variants of these. At least that's my current impression. However, this is also research in progress, so it might be that some of you have beautiful ideas for how to do these things better, and then this may change. I don't think, however, that the number of bugs here will increase dramatically. This is not like a use after free scenario that we're talking about here. So let me give you an outline of the talk. I'll start with a motivation, then I'll talk about historical bugs in libgcrypt, GMP, and OpenSSL's BN. In the abstract of the talk, I mentioned that I would talk about libtomcrypt or libtommath as well. I looked into that for a very long time. There is one known bug in the last 10 years, and I haven't been able to find any other bugs in there that are exploitable, so I have dropped that from here, and instead replaced this with the libgcrypt, which was not in the abstract, but which is also widely used. I will talk about a recent as in patch in January of this year, bug in OpenSSL as a case study to motivate the general class of bugs, and to also give an example of a very common bug pattern. I have chosen this particular bug because it's recent, but also because it is easier to understand than others. I will talk about property-based bug hunting. This is an expression I made up myself. You'll see what it is later. I wish there was a better expression for it. And I will talk about using verification tools to find bugs, and then we'll come to the conclusions. So, the motivation obviously is, or maybe it's to break crypto. The other motivation could be that you want to make crypto libraries better and prove that they're correct. At the moment, my motivation is to break crypto. So, what motivated me to look into this was, there was a paper by Biham, Kameli, and Shamir a couple of years ago that looked into bug attacks. So these are basically problems in hardware-based arithmetic that lead to miscalculations. And so this is a very, very similar issue. But the problem with this paper was that all the examples that are given in the paper are hypothetical. So the only bug that is mentioned that is not hypothetical is Intel's fdiv bug, but that doesn't apply to the examples that they give. So bug attacks are related to fault attacks, which are basically, if you have a hardware implementation of cryptography, you can try to induce faults in the computation by various outside sources, for instance, using heat or using spikes in the voltage. But bug attacks basically use input triggers to trigger faulty computations. So what that means is there are certain inputs for which the hardware implementation is incorrect and gives incorrect output. So I decided to work the other way around and look at the bugs that have been found and patched in BigNum libraries in the last decade, and to see what you can do with them and whether they would be exploitable. And as I mentioned before, I've thought about this for a while, but like the B and square bug that was basically in the advisory in January this year was a trigger for me to look into that again and look into it again more seriously. The other thing is, and this is like an open problem at the moment, bug attacks have only been investigated for the leakage of private keys. However, you can use both bug attacks and BigNum vulnerabilities, also to create signature verification bypasses. And an easy homework for you, and an easy example for you is look at DSA and think about what happens if the modular inverse routine is incorrect and it magically returns 0 for one of the two inputs as 1 or as 2. In that case, you have a very easy signature verification bypass. And actually, it is, given the current state of BigNum implementations, it's not unlikely that these bugs exist. I tried looking for them, but as we'll see later, the tools currently are not in shape yet to prove that they do not exist. At least for the widely used implementations. So what is a BigNum implementation? I mean, maybe you just came in here and you don't even know what the guy in front here is talking about. So BigNum implementations are fundamental ingredients for real-world asymmetric crypto. I'm trying to be specific here because, I mean, there are lattice-based algorithms as well. There are signature algorithms that are purely based on hash functions. There you don't need them. So there are asymmetric algorithms that do not use BigNum implementations, but most of the widely used crypto, so RSA, DSA, most of ECDSA that is out there is based on computing with large numbers. So what an implementation for computing with large numbers has to provide is operations on the integers or in rings modulo integers or in prime fields for addition, multiplication, subtraction, division, and exponentiation, and things like GCD and others. The list can go on and on here. So for crypto, you want to have the above usually in either a prime field or in a residue class ring. So sometimes you have specialized implementations, for instance, for BigNums of a fixed size. So like specialized implementations for 1024-bit or 2048-bit, or sometimes even 512, like if it's a little bit old school, are common. Then you have assembly implementations, highly specialized assembly implementations. So you have people like they try to squeeze the last 1% out of this processor that now supports AVX2. And for guarding against side channel attacks, you also need constant time implementations. So these introduce additional complexity. So usually, like the naive way to implement things will lead to implementations that are not constant time. So that means that you have conditionals in the code that will cause your code to run, for instance, with a different timing for a routine that can be used as a type channel. Or more recently, people have been using cache timing side channels or have tried to evict cache lines. And there have been recent attacks against the predominant crypto implementations for that. But these mitigations that you put in there make the code more complex, and they introduce more opportunities for an attacker to make use of bugs in the basic functionality and also like in the more complex algorithms. So what are widely used implementations? So obviously OpenSSL's BigNum is probably the most widely used one. Then we have libgcrypt, which is a fork of GMP, a very early fork that is used in GNU-PG and GNU-TLS. Then we have GMP, which most people don't realize that it's a problem if it has bugs, but that is exposed in a lot of, there are a lot of scripting languages that have bindings for GMP, and people actually write like homegrown crypto using those bindings. And there's libtommath, which is used in the embedded world because of its very permissive license, so it's in the public domain. So it is used by Dropbear, for instance, which is an SSH server, and by MiniTLS, which is on a lot of embedded stuff. And it's in WPA supplicant. Then we have Embed TLS, which wasn't really on my radar until I realized that it's actually Polar SSL. So what happened there is that Polar SSL was bought by ARM recently, and since then, more optimized implementations for ARM chipsets are going into that library as well. Then we have the Java, the canonical Java big integer implementation that has changed a couple of times in the last decade, but it's pretty stable now. So originally, when Java was written, this was like native code as well that was exposed through JNI. And then they transformed that into a pure Java implementation. So part of that is in mutable big integer, the other is in big integer. Then we have closed source implementation. There's in Microsoft OS, you have beep primitives.dll. If you ever try to figure out where the hell all that computation for your IIS SL handshake is going on, that's where you have to look. There are apparently heaps of other ones, like a heap of other BigNum implementations, but this is the only one I found that is related to crypto that I care about. On OS X, there's libcorecrypto.dll, sorry. This is both on, on OS X and iOS. So this is both on OS X and iOS. And that is an interesting one to look at as well. Very easy to read in assembly. So it's not really that optimized. And for embedded devices, there are many, many others that are homegrown. And they are great, they're very fertile ground for finding bugs in BigNum implementations as well. Okay, so let's have, because I mentioned that there exist bindings for GMP, so you'll have the Ruby BigNums are basically GMP underneath. You have for Python the PyCrypto package, which is one of the more popular ones that binds GMP underneath. And then, like many people like to home roll crypto, then they use Gimpy. In Haskell, the integer type is the standard integer type is integer GMP, which is so you can swap out the integer implementations in Haskell, but almost everyone uses the integer GMP. There's an integer simple as well, which is pure Haskell from what I remember, but this is the default one. And in OCaml, the ZEarth package is the default for arithmetic these days, for BigNum arithmetic. Okay, so let's have a look at the CV, and for that we need to understand first how to square numbers, and we have to go back to high school to see what's going on there. So why do BigNum implementations have dedicated routines for squaring instead of just using the multiplication routine? Because they can do that slightly more efficient. Depending on the number of limbs in the, so limbs is the number of words. So limbs is, if I say limbs, that's words. So limbs is the terminology that is used in BigNum libraries for the individual words in a BigNum. So let's say we have a BigNum that just consists of two limbs, A and B. So A is the high order limb and B is the low order limb. And the word width on this architecture that we're on is n bit. So if we go back to high school and we just split these into two, like so we say, okay, but we'll look at the high order and the low order part individually, then we can basically save one of the terms because we can square the higher limb individually, and we can square the lower limb individually, and then we can just multiply A times B and shift that one upwards. And so we have 3 multiplications. I mean, the shifting is for free, basically, compared to the multiplication. We have 3 multiplications here instead of 4. And I mean, there are many other optimizations that you can do for BigNums, but this is just like, we're just trying to get to the basics here, and that's why this is a very nice bug as well. So when you look at the diff, like where the bug, this particular bug in B n square happened, this is the, so the bug happens in the assembly implementations, but before they wrote the assembly, they had a C implementation that is equivalent, and it's probably easier to show this with the C implementation here, because it's the same bug. So what happens is, like you see here, it squares the high and the low limb. And this macro is supposed to basically compute 2 times, so the middle term of what we saw on the last slide, right? So this 2 times 2 to the n times a times b. We have a macro for that does the multiplication and the addition to a 3-limb word. Now, maybe you can tell me where the bug is. The bug is here. So what happens is that when they try to do the carry propagation, they do the carry propagation in the wrong way, and they drop the carry here. Basically what happens, I mean, you could also say that you have an integer overflow here. So they have this temporary variable that they double, but they just ignore that the temporary variable might be larger than 2 to the n minus 1. And this is a very subtle bug that was present in the OpenSSL code base for 10 years. And it's the same mistake that was made both in the MIPS and in the x86-64 assembly implementation. However, the trigger probability for this, so the fact, like the probability that you will hit this with a random input is low. So you will only hit this with 2 to the minus 64 or 2 to the minus 128 for a random input, right? So that's the, I mean, you might also try to hit it, and then it's like, depending on the algorithm, you can do that. So OpenSSL's impact assessment of this bug was the probability of this is low, and on most platforms, RSA follows a different code path, and hence RSA operations are not affected at all. For platforms where you build OpenSSL without assembly support, for instance, if you have MIPS and you build it without, you can also hit the bug if you turn off assembly support and are on a 64-bit platform. And in that case, their argument is that pre-existing countermeasures that they have in the code base will thwart the attack for RSA because they have RSA blinding. And RSA blinding means that you really have like basically a random number, because I mean, either you can guess the blinding factor already and then you have a different problem, or you cannot make the input such that it triggers the bug with a higher probability than 2 to the minus 4. So either your blinding routine is broken, or the bug is not hittable for you. So the third argument that they make, so they go through the different code paths that they have in OpenSSL. I did the same thing. Unfortunately, they're right in most regards. Static ECDA, they say, is theoretically affected. So in the current, so in the version that was fixed, OpenSSL 1.01K, that is the version that is fixed, and J is the version, the previous that had the bug still. So the argument is that it's only, the only effect of this would be in the point validation routine. So the point validation routine for elliptic curves uses the b n square routine through various other routines. And hence you can construct a point that is not on the curve, and that's a bad thing because you might be able to construct a curve, a point that is of low order, and then you can do all kinds of attacks. But it's not known how to construct these off-point curves at the moment, and all other things are theoretically affected, but there's no exploit known. However, the counter-argument to this is that the impact assessment is only correct as long as you use the OpenSSL crypto routines with OpenSSL BN. And moreover, it's only correct for 101J, but incorrect, for instance, for 101E that was released in 2013 because they didn't have the optimized implementations at the point. So they now have optimized implementations for elliptic curve cryptography that do not use the b n square anymore. And back then they still used that, and hence they have a different code path. And in that case, I'm pretty sure I tried to skip the elliptic curve part of the talk because I was told that might be too technical for here. But this will be in the white paper. There is a related attack that most likely carries over to this. And as I mentioned before, it's not correct when you use OpenSSL BN routines with third-party crypto. For instance, if you look at Android, they use OpenSSL underneath for the Java math big integer. And they have a spongy castle, which is a bouncy castle fork on top of that. And in that case, the arguments here are invalid as well. OK, so that was OpenSSL. And we're trying to gather, I'm trying to go through the different implementations first to gather some bugs so that we can see what the common theme will be. And I have to look at how much time I spent already. OK, so the second implementation that we'll look at is GMP. And this is an older one from 2012 that has the interesting bugs fixes. So there are 3 different kinds here. We don't care too much about the PowerPC stuff, but it's interesting, but it's like it's a niche these days. The first bug is again something in the like multiplication related. It just says 2 bugs in the multiplication code that cause an incorrect computation with extremely low probability without further assessment, and 2 bugs in GCD. Which with a likelihood that is infinitesimally small, which is a very interesting wording for something where you have where you calculate with concrete numbers. So as I mentioned before, they're not just optimizations that you can do in terms of like targeting hardware features, but you can also do like algorithmic improvements. So GMP uses different algorithms for different BigNum sizes. And the reason for that is that for larger numbers, there are algorithms that are asymptotically faster. So that means that, for instance, instead of like an ON square algorithm, you have, for instance, Schönhager-Strasse, which is asymptotically O n times log n. And the bug here is in one of the middle tier ones. It's in the so-called Tom Cook algorithm, and this is theta n to the 1.465 in terms of complexity. So the constant here is much larger. That's why they have like a cutoff point. Only if you have big integers that are bigger than for the core 2 duo, that's 1,400 something bits. Only then this algorithm will be used. And this algorithm is slightly more complicated than the one that we saw in the OpenSSL bug, and slightly more complicated is an understatement here. So it uses basically polynomial multiplication interpolation, and the bugs basically happen in the interpolation phase, and the trigger basically happens in one of the inputs to the interpolation algorithm. And the patch, if we just ignore all of the other things, is these are the in both cases these are the things that are patched in the interpolation routine. And when you look at the functions that are used here, so this MPN decrement macro is actually an assembly instruction on x86, and what it basically just does is it does a subtraction without any carry or without any borrow. Because it's, and the fix is to not use this carryless macro, but to use the proper BigNum routine, the MPN sub. And so again, we see it's carry mispropagation. So they operated on a single limb instead of a whole BigNum. And it turns out that this is a very, very common pattern. It's not just in OpenSL and in GMP, but it's also been observed in ED 2.25.519 implementation. So there's this is like a curve that was proposed by Dan Bernstein, and there's a library called NACL. It's not just like the Google NACL, but this is a same name, different library. That's the crypto library, which uses this curve. And this had at some point also a very similar carry bug. And the same one appeared in Tweet NACL, and there are blog posts about both of these. And what I mentioned before, the BN square in the older OpenSSL implementations, that's one example of an exploit that you can do against against a against an arithmetic implementation. So because I've been talking about big nums now, but you could be more general as well. And you can say, okay, well, there's big numbers, but there's also there are other types of arithmetic. So in principle, what you do on elliptic curve, you have group operations, so that's arithmetic as well. So some people talk about arithmetic there as well. So and this is something that was in OpenSSL, I think 0.97. I'm not sure about the suffix. I think it was Y. So this was in 2011. There was a bug report a couple of years prior by someone from Rode and Schwarz, and nobody had expected that this would be exploitable. And then there were a couple of people from academia who looked at it in 2011. And they found a way to exploit that. And this basically is the first instance of a software bug in an arithmetic implementation that I'm aware of that was turned into an actual exploit that was, in this case, able to recover the private key for an static ECDH exchange. So this is somewhat limiting because static ECDH exchange means that you use the same key over and over with different participants or different runs of the protocol. So if, for instance, you wouldn't, something I very much care about, and one of the reasons why I looked at these bugs is because OpenSSH uses OpenSSL underneath, and that was additional motivation because I want to see what parts can I reach. But for instance, this would not be exploitable for OpenSSH because they don't use a static ECDH. They use a different key. They generate a different point each time. Okay, so now we've talked about the carry mispropagation bugs. Now we want to talk about another. I think this is the unique snowflake at the moment. At least I haven't seen, the carry mispropagation bug is like a bug class, right? So there's many of these. But this is this got me scratching my head for a while. So there's this commit in May 2014 by Werner Koch, who's the author of libgcrypt and GNU-PG. where it says like fix a subtle bug setting spurious bits with MPI set bit. And this is also a bug that was in the library for a long time, and apparently they had it had been triggered a number of times, and it was not realized that this was the underlying bug. So what's called Heisenbugs. So apparently there were some things that were not properly debugged here. And the reasoning for that he gives is that it is only triggered in 1/6 due to different memory allocation patterns, which does not really make sense to me because the allocator that they use is the system allocator, so it is more likely that they may be using a different version of glibc, or maybe he went to a different architecture there. Anyway, if you read the commit log and you look at the code, it's a little bit hard to believe what's going on there. So they have a routine for setting bits in a BigNum word, and they allocate the BigNum at some point, but they don't clear all the bits under certain circumstances. So what that means is that you can end up leaking data from uninitialized regions of memory using that bug, but you can also force bits to values using heap primitives. So that's like predominantly in the multi-threaded environment case. So this would be more like if somebody used Apache with GNU-TLS than like if somebody used like OpenSS, used GNU-PG in a mail client. But the exact impact there depends on the allocator. And this is still not completely understood by me. So, because they claim this bug has an effect on the library. And the only way I see how this could have an effect on the library, the only way where I see this routine being used is in the DSA generation for the value k, which is a very, very sensitive area. Like, this is something you totally don't want to screw up. And the comment there is even more interesting because they say, make sure that we have the requested number of bits. This code looks a little bit funny, but it's easy to understand if you consider that MPI set high bit clears all higher bits, which is not the case. So like whoever put that in there, I don't know. And then they set it and they cleared again to make sure it has the right size. But to me, it looks unexploitable because it has the right size, because what comes in here is like a random number that is of the right size already. I don't see how this can happen. So more eyes are needed here. I don't there is the claim is that this has been observed in practice and this bug has been triggered. But besides this, there's only the prime generation routine, and it's not. I don't see how how that would happen. This is the only place at the moment where I see that this could have an impact. Okay, but this is like a unique snowflake. I haven't seen that kind of thing in other implementations, but if you have that, that's a very interesting bug. Now apparently I have mixed up the order of slides, so I have to put that before. So we've talked about these bugs and how they have been randomly found by other people. Now we'll talk about whether there are maybe more systematic approaches to finding them. And one approach that you can use is unconstrained symbolic execution. So that's something that was proposed by Ramos and Engler. So Dawson, Engler is one of the more well-known people, or I think the most well-known people for this type of work in the academic community. And basically, what they proposed in this paper from 2011 was that you can use symbolic execution. So, okay, well, let me start again. Given that you have different implementations of the same routine or the same operation, you can use symbolic execution to prove that they're either equivalent, so then they all have the same bug, or they are all correct. And in equivalence, on the other hand, if your symbolic execution engine shows that you have an inequivalence, you automatically get a test case for triggering the behavior. You still have to figure out which one is the incorrect implementation, but in case of BigNums, I mean, that's a little bit, that's easy, right? We know how to calculate that. We've been doing that for a couple thousand years. Numbers weren't so long, but like, this is like, we can figure out which one is the right and which one is the incorrect algorithm. So the tool that they built is not publicly available, but for our needs, the approach is easily reproducible using CLI. So CLI is an open source symbolic execution engine, and that can be used for this. Obviously, you're not gonna compile all of OpenSL, then just run CLI against say mod X. Mod X. You will have to need like individual functions that you run it on. And what you then do is you take different BigNum algorithms, different BigNum algorithms and match them against each other, but you can also take different implementations. Just have to make sure that you write basically routines that use canonical representations in memory, so otherwise you can't compare, obviously. But there are some challenges. So as I said, like a lot of these more widely used implementations use assembly code, and that assembly code, if you want to do that, needs to be accurately lifted to LVM. So because like CLI is based on symbolically executing LVM code. So in another project, we used such a tool. So ECDH, which is a company based out of San Francisco, has built something for that. Trail of Bits out of New York have also built something for x86 to do that they released publicly, so that's Maxema. And ECDH has a multi-arc lifter that works for different architectures. But one thing that you have to bear in mind there is that the lifter will need support for instruction extension as well, and this has to be it has to be accurate support. So I mean, if you screw up there, then you either find bugs that are non-existent or you miss a lot of bugs. And so I have to go, because I mixed up the order of slides here. The other option that appeared while I was, after I had submitted my talk, is there's a company out of, I actually forgot which part of the US is Galois. So Galois is basically a company that has been doing contract research and development for the NSA. And they developed the domain-specific language crypto a couple of years ago for specifying cryptographic algorithms and then proving correctness. And the Galois software analysis workbench is a very interesting thing that appeared, I think, like 3 months ago or so. And this is a tool that allows program analysis on LVM bitcode and Java bytecode, and it allows cross-language equivalence proofs as well. So you can either have like implementations in, say, in C or C++ that you compile down to LVM, or you can have like Java bytecode, or you can mix and match and try to show that they're equivalent. And this also leverages symbolic execution, and they use something called SMT-based verification, which is a Haskell package, and that supports different SMT solvers, and you can figure out which one is best for this. In my tests, it looked like Z3 was winning here for BigNum. The code base is somewhat alpha quality. So for instance, it can only handle integer arguments in the LVM functions. But I mean, it just means that you have to tweak the code before you try to prove correctness or find bugs. And the code is available on GitHub and free for non-commercial use. For commercial use, you have to contact them. And yeah, I found the timing of that interesting. It looks to me that there are people who are also very interested in having correct implementations of crypto. But the more surprising thing to me was that something else works. Namely, it's an unfortunate name. I call it property-based bug hunting. it's a version of fuzzing. So assume that you want to find bugs with a fuzzer. And when I thought about this, like this will never work, but I should try it. So you have axioms for arithmetic operations that you can check. For example, you have the axiom in a prime field that if you take the inverse of a number and then you take the inverse again and it's not, the input is not 0, then it should be the same number. Or you have two functions, like this is the case that we were talking about before, the square routine and the multiplication routine. And if you take the square, okay, there's a mistake on the slide. So if you give the a comma a to the function g, then that should be equivalent to giving the argument a to the function f. Completely screwed that up, sorry about that. And now, how do you randomly check for many inputs fast? Well, just fuzz it. And what you do is like you cause crashes on inequivalence. And it turns out that AFL fuzz is able to find the b in square bug with this little bit of code in like less than an hour on one Xeon. And yeah, as I said, like I only talk about old days, but you can try this with different other properties and other BigNum libraries, and you'll maybe find something as well. So conclusions. BigNum vulnerabilities are real, and they can bite you. I think the medium-term goal that we should have is that we want to have formal verification for the arithmetic underlying cryptographic primitives. And for that, like optimized assembly is like a real significant hurdle, so I think we should just do away with that. I mean, if we want to formally verify something, I just skip the assembly. I mean, also, I mean, they are like these great instruction set models for x86 and ARM, and you theoretically can do that. I mean, it's not worth it, like the couple of percent that you need that you get there. Also, that's a more interesting problem. Like, if you have countermeasures for side channel attacks, that increases the complexity. So then the question becomes like, assume that you're at a stage where you say, okay, well, either I'm going to prove correctness or I have side channel resistance. That may be a call that you have to make individually depending on the application. And my takeaway from all this is that libtomcrypt and libtommath are very, very nice to read. The only bug that was found in the last 10 years there that's publicly documented is one in the prime generation routine. So they screwed up. Instead of like doing Miller-Rabin a number of times, they only did it once. And the interesting, I laughed when I saw the commit log. So this bug was found by Mark Karpeles, the founder of Mt. Gox. So yeah, that's it. This is the bibliography. I hope nobody fell asleep during the talk. And if there are any questions, feel free to ask. No, I did not.
Even better, do you think it's unlikely that these kinds of problems, it looks like carry propagation,
yeah,
really crappy JavaScript?
Yeah, no, I didn't. No, I tried to like I wanted to look at the ones that are like really widely spread, that have like that have been around for a long period of time, and in my experience, like full disclosure, like when I was in university. I also wrote like my own BigNum implementation, and I had students that wrote BigNum implementations in a course that I was an assistant for. And like carry propagation is it's just like every second student would make that mistake, and I would not be surprised, not at all, if like every second like JavaScript implementation had some variation of that.
Is the best bug you get practice from that the point after thing?
No. So I mean, how many JavaScript implementations do like RSA blinding? Any? So the second question is like, what's the usual, like, what's the word width for JavaScript implement? So I mean, they only become really hard to hit because you have you have the low. I didn't go into the failed research. So there's a lot of failed research for this as well, namely like how to exploit this and what did not work. But that was mostly failed research because I concentrated on these particular implementations, and it's much more likely to succeed in other cases. And this is also something that is documented in the white paper. I can't go into that in this talk, however, because it would be multiple hours then. Maybe. I cannot really talk about that, but maybe it was not so failed research there as well. That's not in the paper either. This is not related to this talk, however. Or are you talking about like? Yeah. Okay. Yeah. Yes. That's correct. No, but that would mean that that would require accurate modeling of the allocator as well, and I have not done that. No. I was using the symbolic execution tool basically to compare different implementations. And that did not work so well. So it only works well if your routines are really small. So if you try to basically compare the Bn square against the Bn mul in OpenSSL, and even if you have a low number of limbs, like if you try that with 3 limbs, it did not work for me. So that was why I was surprised that it worked like with straight up fuzzing. Yes. Yeah, I know, and it would be much more interesting if I could do the memory modeling as well, but I think we're not quite there yet, at least with the tools that we have publicly available at the moment.
I think you just answered my question. My question was, with the symbolic execution, wouldn't that lead to a state explosion? Because what I think I know about symbolic execution is that it rarely works in practice on real-world software because there are so many states. But you just said it didn't work for Bn square and functions like it. Yeah.
But it can work for other things. So it did show that other things were equivalent.
Did you find bugs with it?
No.
Okay.
No. So that's the sad part.
You had the 2 axiomatic examples of this.
Yeah. Yeah.
Do you have a big library of those equivalents that you're using?
Say?
Is there a small number of axioms that you're fuzzing against, or do you actually have a relatively large number of axioms?
I have a small number of axioms, but I have a large number of properties. So these were just examples. So they are the easiest one to show in a talk. So. Any more questions? But I mean, you can with the properties you can really go wild. I mean, it's just like you want to have invariance of some kind as well. More questions? Any heckling? Okay. Okay. Yes. Okay. Okay. That's correct.